All right, so let's remind ourselves what we were up to last time. So last time, the basic idea was we were trying to get a relaxation solution to work. Relaxation as applied to the Higgs mass. And we had gotten basically almost all the way to the answer. The idea was you make Higgs mass a function of something, function of phi over f, and then you make sure that v of phi at its min has m Higgs squared approximately 0. Okay, so this was the approach. And at this point, there was a bit of a leap of faith. I basically said, trust me, I'm going to write a model, and after a bit of math, you'll find it has this property. The basic idea was there was, it could be any number of standard models greater than, or Higgs is, I was saying. We had H1, H2, H3, and H4, all of which were cyclically exchanged in a Z4 symmetry, and could actually be a Zn symmetry with anything greater than or equal to 3. And we had an angular field, phi over f, which transformed as phi over f plus 2 pi over 4. We needed this symmetry plus 1 spurion, and then we just did the standard DFT thing of writing everything allowed by symmetries and just seeing what happened. The last thing was a spurion, kappa squared, which goes as kappa squared e to the I alpha. Let's see, phi over f. I think I've had a minus sign last time. And then we just said, write the most general Lagrangian consistent with all symmetries. That's renormalizable. After a lot of suffering and a lot of math, what we found was v as a function of phi looked flat-ish. And then it's periodic. It wraps back to the other side. And we found that at any of these points, which were sort of minima, we had a Higgs mass equal to 0. Whether it might be like the first, second, third, or fourth Higgs masses. Okay. So this was all nice and good. There was, at one loop, or at tree level, this was perfect, could just solve the entire problem. At tree loop level, turns out there was an additional potential that sort of pushed you actually not exactly to the there. And so we had found that we could help by about a factor of 100. Okay, so we are not done with the story because one, I have only talked about Higgs's. I have not talked about standard model or anything like that. So we actually have to, one, finish putting in the standard model to everything, and two, start comparing to experiment, right? It doesn't matter if this mechanism even worked for the big hierarchy problem if it's excluded, right? Our whole goal was to find something not excluded, so this would be a failure, maybe an honorable failure, but still a failure nonetheless if it was completely excluded. So, let's see, first things first. We just say we actually need the rest of the standard model. We just don't have Higgs's. And so there are several options. Well, we need a Z4 symmetry. So the question is, how does everything in the standard model transform under the spurion symmetry and the Z4? The spurion is easy. Under the spurious symmetry, nothing transforms. Nothing. This is all about arranging how phi couples to the Higgs. Who cares about the rest of the standard model, the tops, the quarks, the leptons, etc.? Nothing. And then there's the Z4. So there's basically just two simple options. It's either nothing, the standard model does not, the rest of the standard model does not transform, or 4 standard models. We can actually go over a little bit more detail whether or not you have to copy the entire standard model or just pieces of it, but we'll see. So first things first, what happens if you do nothing? If you do nothing, this means these guys all have the same SU2 charge and U1. So this means you have a single SU2 weak times U1 hyper, and you have your Higgs, and you have the Z4 symmetry means 2, 3, you have 4 of these guys. And so what happens with, for example, the whole point of the Higgs boson is that it gives mass to the W and Z. So what happens to the W and Z masses? Well, whichever one has the largest VEV does the work. Notice this region has all negative. So everyone has a VEV. So MW squared is G squared. I think there might even be a factor of 2 here. V1 squared plus V2 squared plus V3 squared plus V4 squared. And you'll notice what gives the W boson the mass? The guy with the largest VEV, not the smallest, right? We arranged one of the Higgs guys to have a very small mass. And so if this guy is small, all the other ones are large. And so clearly this is going to be a problem because the small guy is going to be doing nothing for the W and Z bosons. And so we have an issue, which is it doesn't really couple to the W's and Z's. It's not responsible for their mass. So this is just very excluded. The Higgs boson is what gives the mass, not some other crappy heavy guys. So this is excluded. And so we just then proceed and hope that the whole model isn't just completely dead. You have 4 standard, you start saying, well, how can I fix this? What if I have multiple SU2s? So each guy gets their own SU2. SU2 times U1. Then there's a new SU2 times U1. Dot, dot, dot. You have your Higgs 1, which is nice here. Your Higgs 2 is couples to its own SU2 and own U1 hypercharge. And then we're fine, right? Because then our W boson gets its mass entirely from us. Maybe it's 2. Oh, whatever. Not going to be doing 2s right now. And so now it's good because now the Higgs boson here, the light guy, actually couples the same way us. But do we have to copy anything else? Well, unfortunately, anomaly cancellation is very, very specific in the standard model. And if you just try to copy parts of the standard model, you screw up pretty much everything about the standard model. So anomaly cancellation forces us to do color. If you have multiple SU2s and SU3s, you're going to have to copy the quarks entirely separately too. So you just basically have the entire standard model, 1, SM2, SM3. So we are basically forced to copy the entirety of the standard model. Okay, such is life. is it still okay? Still, is it excluded, right? We really want something that works. So we continue to go on and just say, we have a lot of probes of everything. Are any of them constrained by anything? So first we just want to say, are we alive? And the easiest way to see are we alive when we write a model is, can you make everything as weakly coupled as possible, right? Because if they're copied of standard model, there are definitely things like, say, like massless particles, like there are photons, there are very light neutrinos, so I can't make them super heavy, so impossible to produce. The best case I can have is making them very weakly coupled. And so so if I wanted to kill the model, I could just add terms like epsilon F1 kinetic mixing between the photons. Then the fact that they have an electron means that there are new light charged particles, which is going to be a bit of an issue. However, you can ask the opposite and just say, what do you need to make the model work? And the answer is, the only thing you need connecting these sectors is the scalar phi, right? Because this guy is what relaxes This guy is what relaxes the Higgs boson, and the structure forced it to talk to all four Higgses. So notice it couples with strength 1 over F. And so you can sort of imagine, well, if that's the case, you can quite see how it would be quite difficult to produce all of the other guys, right? If F is, let's say, M Planck, right? What do we actually need in this model is we need to be able to relax to the minimum. So we just need Hubble at some time we care about, let's say BBN, to be larger than the mass of phi. That's all we need to relax to the minimum. And it turns out to be a very weak constraint because this has 1 over M Plancks in it. So you can very easily arrange for Hubble to be larger than mass just by taking a large F but not M Planck scale. Okay. So turns out that this is great for keeping you from collider constraints and supernova or any late time physics. But as people have probably started to realize in their own research, there's a lot of other constraints on models, in particular cosmological constraints. So what about cosmology? And here you can see that there is potentially an issue that really does need to be solved. So let's just say we had a Z4 symmetry. So let's just try to do everything nice and symmetric. So you have standard model 1 at some temperature, standard model 2 at the same temperature, standard model 3 at the same temperature, standard model 4 at the same temperature, right? Just be like, this looks nice and symmetric. Our early universe cosmology starts off like this. What does this mean? This means today, standard model is 1/4 of a bunch of other energy densities, which, okay, there's things like dark matter around. We're not the big fish in the pond. That's fine. What is annoying is not today, but at, let's say, BBN or CMB. Because we have measures of N effective, and we know delta N effective is less than about 0.3. And you can ask, what is the total N effective that comes from an entire standard model. There's definitely 3 from the neutrinos, and there's also the photons. And all of these things have spin. And so the neutrinos by themselves, from a single standard model, are already 3. And if you triplicate it, that's 9. You're really screwed, right? And so you most definitely have to say, so I can even start writing down issues to solve in such a model. So problems / opportunities. One, cosmology. Right? What is the cheating way out of this, which is something you should not be doing? Cheating answer would be something like, well, I guess you could do it. It's just a little unpleasant. It's just say, well, whatever. The initial condition of the universe is just one of these guys randomly has a temperature, T, and the rest have zeros. And we just happen to be lucky enough that we were the one that had a temperature. 1 in 4 chance. Okay, if you were solving the entirety of the hierarchy problem, 18 orders of magnitude, sure, a 1 in 4 chance is fine. But if you only are getting a factor of 100, you might want to hope to hold yourself to a higher standard, right? The more you accomplish, the more ugliness you're willing to take. This is just a general rule of thumb. And if you're playing for only a factor of 100, maybe you might hope to do something better than just pure luck. Okay, so that's the first thing. I guess we'll actually get to a solution to it when we talk about something, a different model. What else? Let's go back here, let's say. What else is you should be careful. I have been sloppy and no one has called me out on it. And so I will call myself out. So you can see this entirely at the pictorial level. I had said our starting point at tree level, flat, MH, all M Higgses are less than 0, but in particular, MH1 is less than 0. And then suddenly shoots up when the Higgs mass becomes positive. If I push slightly to the right here with a potential, where is the minimum going to be? It's not going to be here where the Higgs mass is negative because there's no first derivative, right? The minimum will be poking a little bit into here where there's actually some pushback, right? So the minimum is over here with small positive Higgs mass. So another thing, make sure never to convince yourself with words. Always do calculate everything afterwards. Here, positive Higgs mass. We got a small Higgs mass, which is good, but the problem is positive. Higgs mass. Okay, let's see, anything else? So I would say these are need to be solved problems. Need to be solved because if you don't solve these, you are excluded. And while it's nice to write a paper that solves a model, if it's excluded, then you're in trouble. what other things? So are there any conceptual problems that you might want to address? So here, conceptual. Okay, so yeah. Yep. Yeah. With a slightly heavier Higgs mass, but yes. Or a factor of 100 or something like that. Excellent. So if these guys were never around, you'd have no problem. So the question was, let's say we just look at the second line here. Let's just start here, but this is going to infect here, and you get some T nu here, which is small, some T nu here, which is small, some T nu here, which is small. And you can be like, even if you started off in your best case scenario, well, maybe say this is us, so I don't need to rewrite this. These are all a bunch of dark sectors. Even if I said there was no temperature, no energy, nothing of them around, right? If there's nothing of them around, there are no bounds from at least astrophysics and cosmology. But that's not consistent to just take them equal to 0 and then live with it. And so you have to estimate, is this a problem? And so let's just estimate quickly how much energy enters here. So if people haven't seen these estimates, they're actually pretty fun and relatively simple to do at the order 1 level. So if you're a dimensional analysis person like me, you can skip a lot of the order 1 numbers and just see. So the question is, first, what does a cross section that takes us to them, and you look at the cross section? Well, the dimensional analysis I had said was us goes through a phi to them. Each has a coupling 1 over f. And so this cross section is proportional to matrix element squared, which is 1 over f to the 4th. And then we say, well, this has the wrong units for cross section. Finish everything else with temperature. Okay, now it has the correct units. And what you can see is if I compare n sigma v, so this is the number density dt of them. This is them. So yeah, you want to ask the production rate of them, n sigma v, which we're going to compare to Hubble. So the rate of production, ddt, is, we're just going to get units of time. So this is going to be what? T to the 5th over f to the 4th. This is in units of inverse time. So gamma is 1 over this stuff. We need to compare it versus Hubble, because that's how much time you have, right? At any given temperature, the amount of time you have is, or 1 over time is Hubble, which is t squared over m Planck. So if our goal is to argue that we're not excluded, we always be like, I'm going to be as optimistic as possible. The hottest the universe ever gets, T max, I'm just going to take to be BBN. And we'll see how safe we are. So this is MeV or so. So technically speaking, in case people haven't seen this before, BBN actually starts after MeV, but at MeV, several things occur. The most important of which is that neutrinos decouple. So N effective in everything. This is really more an N effective type constraint than BBN, because BBN happens more at like 100 keV, but minor details. Everyone will still call it a BBN constraint. And then we say, if this is so long that in a Hubble time nothing happens, you don't even get a single scattering event, then clearly we're not going to produce any of these other guys. So we impose that the time of this is longer than the time of that. These are 1 over that. So I think we're imposing the opposite. We need t to the 5th over f to the 4th be less than t squared over m Planck. So this is that nothing ever happens. And then we just say this is MEV. So we need f to the 4th greater than, what is this? T cubed over, wait. T cubed times m Planck. Which is, let's work in units of GeV. So this is 10 to the minus 9 GeV cubed times 10 to the 18 GeV, which is 10 to the 9. So F is about 100 GeV or so. There are going to be other better constraints on F, because a scalar that interacts with the Higgs via 1 over F coupling does things like mediate fifth forces, it does things like Higgs mixing, etc. And so we're going to have better constraints on F than just 100 GeV or so. Yeah. But if you want, just set it whatever to F to 10 to the 8 GeV, 10 to the 9 GeV. That makes you roughly safe from supernova bounds. And then you'll also be very safe from colliders at that sort of Fs. Yeah. And so another great thing about dimensional analysis, tells you when you don't have to do a careful computation. Yeah. Yeah. So you want to ask, how does this more quantitatively lead to an estimate there? Okay. This is MEV, so that's 10 to the minus 3 GeV. So T cubed is 10 to the minus 9 GeV cubed. M Planck is 10 to the 18, so this is 10 to the 9. And then I took the 4th root, which is about 100 or so. Yes. Yeah, so you can ask, here I didn't actually ever compute the temperature of the dark sector. I just said the rate, I never produce a single dark matter particle, or a dark sector particle. You could ask, well, there are a bazillion particles, even if you, an average one doesn't produce one, there might be a little bit leakage. And if you want a slightly more concrete way, you say d rho in the dark dt, this is the Boltzmann equation, is rho sm squared, or n, sorry. God. N sm squared sigma v times the temperature. This is, roughly speaking, what the Boltzmann equation is. And if you rephrase this, you can say d rho dark dt 1 over rho standard model is this gamma. This is the n sigma v I had before. I now just say, screw the integral, multiply by time, a poor man's way of doing the integral. You get rho dark over rho sm equals 1 over t multiplied by t, gamma over Hubble. And you can see if gamma is much smaller than Hubble, the amount of dark energy compared to the standard model is very small. If we're saying things like, oh, this should be n effective type things, you might actually say, no, it's not less than 1, it should be less than like 0.3 or whatever. But your order 1 errors are going to be larger than that. So if this matters, you're going to have to actually do it carefully. Yeah, but this is, if you want a slightly more quantitative way of doing it, is how you would say it. All right, anything else? Okay, great. Okay, so are there any conceptual problems? I guess I should point out, have these problems been solved? There are, I think I know of two ways of doing this, solving the cosmology. There was the get lucky that I was not a huge fan of given the numbers we're playing for. I would say get lucky is a perfectly valid excuse if you're solving the entire hierarchy problem for a 1 in 4 accident. But that's not the game. The other way is there's a trick that I'll talk about when I talk a little bit more about naturalness, which is asymmetric reheating. It is entirely possible to populate only the standard model with the lightest Higgs boson because, for example, kinematics are very different between the the 4 sectors, right? If one of them has a bunch of heavy Higgses, another one has a lot of really light Higgses, it's pretty easy to decay to the light guys, and it's pretty hard to decay to the heavy guys. So it's quite easy, even if everything is exactly the same, a Z4 symmetric, to decay into the light guy. And so I'll sort of talk about it a bit more later, but this is a solved problem. There's also small ways to get yourself a small negative Higgs mass. They're not pretty, so I'm not going to say it, but other than they exist, and it'd be nice if someone thought of a better way. Okay. All right, so what are some of the conceptual issues, at least I have with this? And I would say I have two conceptual issues with this problem, none of which are necessarily even conceptual issues with the problems themselves, so much as my unhappiness with how I got here. So you'll notice I had a great idea, copy a solution that we've seen in nature before, many, many times. In classical mechanics, relaxation is how everything is solved. Well, that and having a finite size. Those are basically the two ways almost all naturalness problems are solved. And you'll notice when I told this model, I basically said, great idea. It was like, great idea. And then I said, here's a model. I didn't tell you why I chose this model. I didn't tell you anything really other than just, here's a model that works. If anyone does this to you, it means they don't understand why the model works. They just said, I calculate it, it works, shut up. That is, okay, it works for some people, but not for me. And so, for me, why does this work? And to me, why does it work or not work will basically tell you why, or is it possible to get around this factor of 100, right? I'd said this sets m Higgs less than the normal value or natural value by some 2 orders of magnitude or so. Of course, ideally, I would like to take this and turn it into whatever, 10 to the minus 18. I want to go all the way from the Planck scale, right? And if I don't understand why the model works, how am I supposed to change it and make it work better? And so I think this is one of these conceptual things where it is it's maybe not talked about, but if you're a model builder, this is actually an important thing to actually understand why a model works and basically how to poke it and change things. And so as a result of this why, there's basically, as far as I know, just one model that does this, which is very unsatisfying, right? Because I told you there's an infinite number of supersymmetric versions of the Higgs. There are infinite number of composite Higgs models, even relaxion and all this other stuff. There are like 20, 30 types of models for all of these things. This guy, there's one, and it's either the first or the second most common way that naturalness problems are solved in classical mechanics, right? This is just weird. It should be like compositeness, where things have finite size, that there's just an infinite number of crappy models. And there's one. So clearly, there's something conceptual going on here that at least I completely miss. And I think probably other people are in the same boat. So this, to me, is the main conceptual problem here that at least personally I would really like to see solved at some point. Okay, so this is roughly it for relaxation models. Did people have any questions? Yeah. Ah, excellent. So you're just saying, I have some spurion structure. How the hell do I UV complete it? Yes. That is, I guess, a problem / opportunity I should have written for all of the models I've been mentioning so far is, does this make sense from a UV perspective? So what were the things required for a Z4 symmetry, or even the spurious symmetry I wrote before? Okay. So Z4 symmetry. So Z4 symmetries, let's just get our scalar. So let's say we have a U1 that's spontaneously broken by a scalar of charge 4. This means phi equals some vev e to the I Goldstone over F. And you can ask, does this break the symmetry entirely? Well, this has charge 4. So if I rotate this, it goes e to the I 4 times alpha. And in particular, if I choose not a 2 pi rotation, don't choose 2 pi, but I choose 2 pi over 4, so I go 1/4 of the way around a U1, this is equal to itself. You have a e to the 2 pi I, which is 1. And so this breaks my U1 down to a Z4. And you can see, for example, that phi here is constant. And so you can be like, great, I get the symmetry structure I want. This is not the phi I called before. So maybe I should call it some pion. So let's call it pi. E to the I pi. Crap. Okay. You can now ask, well, under my Z4, I had said phi over F goes to phi over F plus 2 pi over 4. So in other words, what I need is when I do my Z4 transformation, I need the charge of the object not to be 4. So I'm just going to add another scalar. I don't really know a lot of good names for scalars, I realize. I'm going to call it x with charge 1. And now, when x gets a vev, v prime e to the I phi over f, it will spontaneously break Z4 down to nothing. I'm just going to take v much larger than v prime. So my EFT will just have a charge 1 guy under Z4. And under Z4, this goes to e to the 2 pi I over 4. This is exactly the transformation I had here. Okay, so that's at least a way you can get the spurious transformation symmetry. Is there an easy way to get 4 standard models out of something like this? I don't know. I know how to get an infinite number with an extra dimension. I don't know how to get a finite number. This is one of those weird cases where people are more happy with infinities than order 1 numbers. If you add an extra dimension, you can get a full U1 symmetry with an infinite number of new particles, all phi at each of the direction in the new fifth dimension. And people are perfectly happy adding an infinite number of new particles, infinite number of standard models, etc. But if I decide to say my extra dimension is just this, it's not a very good extra dimension. It only has 4 points. People are a lot less happy. And, well, my heart sort of agrees with them a little bit, but I also don't see the exact logical reason why I'm happy with infinity and not happy with 4. So, yeah. Yep. Let me think. So, I don't remember how close the neutron masses have to be. There's a quantitative statement that will answer your question, which is the following, which is, I can do things like just say, this is an EFT, so I write everything consistent with symmetries. So I can write UDD us, UDD them. Let's call them primes, whatever. And this is a dimension, what? 3 halves times 6 is 9/5. Some UV cutoff to the 5th power. And we were gaining, what, a factor of 10 or 100. So this is few TeV to 10 TeV, which is roughly where the current neutron sort of bounds are. Order 1 matter a lot when you take it to the 5th power. So this is actually not the best way of doing dimensional analysis because a 5 here to the 5th power changes things by a lot. So I don't remember what is the number you need here to make it work. You also need these two masses the same or close. And then that's just a statement of if the Higgs VEV was TeV scale instead of 100 GeV scale, what would the QCD scale be? It wouldn't change by much. So there's a good chance these are still fairly degenerate. The only question is a numerical one, whether or not this number turns out to be large enough. And this is one of those cases where you would actually have to sit down and write the number a lot more carefully than I've been doing so far. Yeah. All right. Excellent. So what you would say is, you can draw a nice picture for a lot of these things. Let's say this is alpha strong versus your RG scale. This is the standard model, or standard model 1, which is us. And you say, whoops, at high energies, there's a Z4 symmetry relating everyone. So standard model prime is exactly on top of us. This is SM prime now. But when things, let's say like the top quark, get integrated out, let's say here is M top prime, it gets a kick and goes up as you integrate all of its guys out. And so this confinement scale, lambda, that's not a lambda, lambda QCD prime, is going to be different than this just due to the beta functions, due to matching, integrating out particles at different scales. And from the Higgs, it would be basically the same, yeah. And so it's just in some sense here, by chance, that's how we observed everything. And so that's the leading effect, yeah. All right, anything else? All right, so since I can do it, crud. I only have 10 minutes. Okay, so let's just actually call it here a little bit early, and then we'll sort of go back later today and start talking a bit more about asymmetric reheating, or maybe I'll use the time to think and decide to skip that and talk about something else. But all right, I guess I will see you guys after the break. Yep, all right. Okay, everyone. So what we're going to do next is very briefly talk about asymmetric reheating. And in particular, we're going to talk very briefly about a different historical solution. It'll be relatively quick before we get to my favorite subject of human stupidity. So the last historical solution. So there are two classes of historical solutions that I know of, the relaxion, and the other is called naturalness. And so we're going to talk about it briefly, mainly focusing on this aspect of asymmetric reheating, since this asymmetric reheating shows up in a variety of different models, some not even related to the hierarchy problem. So it's worth mentioning it at least once or twice. So just very briefly, what is the idea behind that at least inspired something called naturalness is the following. Let's say we have a bunch of scalars with masses, sum over I. They have some random crappy interactions, I, j, k, and maybe some quartic couplings, right? So a bunch of scalars. By chance, if I just plot m phi squared, some of them will be heavy, some of them will be large negative, and I'm just going to have a bunch of them thrown in here, whatever. So just a bunch of random ones. I guess by chance I drew one closer to 0 than I had thought I would, but by chance one of them is going to be small. And the question is, well, in this case, I just threw a bunch of darts. Fine, one of them happens to be light. However, the problem is then, why in the universe around us do we see the light guy? Why do we see the one that looks lighter than it should be? And the answer is, well, whatever. I started off with all of these scalars, and then they started decaying. Yeah, all my heavy guys decayed into light guys, decayed into light guys, decayed into light guys. Eventually, everything ends up in the lightest state. And so, in some sense, this is a way to get a very light guy using history, which is just all the heavy guys are unstable, right? It's a great idea of just solving all hierarchy problems is just one guy happens to be light, everything else decays to it, and so, well, that's what we're stuck with, right? This is a great way that history can explain why we're in the situation where the Higgs that we see around us happens to be light. Okay, so great for just a random scalar. How great is it for the standard model? Turns out less great than you would hope. What is it that makes the standard model hard? If I just replace these scalars with just standard models or something like that, we have like some mass scales, we have some heavy standard models, some lighters, some lighter, some heavier again, and the hope is just like, oh, well, maybe we can go like this, decay our way all the way to the light guy, which is us, and great, that would be awesome. The issue is that standard model has photons, so this does not make sense. It does not make sense to say, here's a heavy standard model, because every single one has their own photon, which is exactly massless, right? And so, in practice, great idea. The standard model is more than just a dinky little scalar. It has massless particles or very, very light particles, which makes this pretty hard to implement in practice. So the idea of asymmetric reheating is to be like, okay, fine. They all have their own massless scalars. Maybe decays are not the way to go. Instead, the idea is to be like, well, maybe the temperature of everyone is 0, and whatever the inflaton does, you have inflation over here, and it decays into the light guy more than all the heavy guys. Even though everyone has massless photons, somehow this guy is like, I want to decay to the standard model, the light guy more than everyone else. And so this is why, one reason why you might care about asymmetric heating. This was another. There are plenty of dark matter models where people care about asymmetric heating. It has nothing to do with any of this. And so let's just very briefly talk about asymmetric reheating. Okay. So asymmetric reheating. We want to do something in a way that treats everyone the same. So we're just going to have a scalar, phi, and give it a coupling to all of the Higgses. Now, you can ask, if this inflaton guy decays and reheats the universe, does it do it with the properties I wanted, right? Does it go to the standard model more than heavier standard models and things like that? And we can just start drawing Feynman diagrams. Scalar phi, let's say its mass, I'm just going to choose to be 200 GeV. Let's say, not 200, 280 GeV. I'm going to judiciously choose it. And it can decay to two of my 125 GeV Higgses. H dagger. Great. But let's say the next guys are heavier. Then it kinematically cannot decay into their Higgses. And what happens? Here's some heavy Higgs. Let's say the heavy Higgs gets a VEV, V prime, 1 over m h prime squared, and to two of their fermions, y fermion. Clearly, this is suppressed by v prime over v squared. So roughly speaking, this gamma is suppressed by 1 over VEV of the Higgs squared, taking this to be roughly 1 over v squared as well. Just being a little sloppy with order 1 numbers. So you can see, the heavier the guy is, the more the decay weight into it is suppressed. This has, I guess, a y fermion squared. And if you want to get dimensional analysis correct, this has kappa squared m phi. And now it looks like the units are correct. Okay. And you can see I get additional fermionic suppressions. I get tree level decay into us. Great. This very much favors light standard model versus everyone else. So this is just the basic idea behind asymmetric reheating. In fact, you can be like, well, what about the photons in everyone's sector? And in fact, the easiest way to study all of this turns out just to be like, write the effective operators, coupling everything phi here to the photons. Just be an EFT person. That's the easiest way to deal with everything. I want a phi decaying into 2 photons. The coupling of phi always comes with the kappa here. This is a dimension 4, 5, 6. So m Higgs squared. You can see the decays into the photons of the lightest Higgs is still more preferred than the decays into the photons of other guys, even though they're all massless. You can draw Feynman diagrams and get this. This is just pure dimensional analysis in the form of writing an EFT coupling of phi to the photons. So main point of all this, quick diversion, is it's very easy to arrange for things to decay into the very lightest sector. And naturalness is not the only reason people care about this, so I thought I'd at least mention it briefly. Okay. Any comments or questions? 4, 5, 6, yes. So kappa, look up there, I defined it as kappa phi h dagger h, and so it has dimension 1. And if kappa goes to 0, it couples to nothing, so kappa here has to appear. Yeah, and so that makes it even more suppressed than you might have thought otherwise, because without the kappa, it's a dimension 5 operator. Yeah, okay, great. Okay, so let's go back to the beginning of yesterday when I was talking about the hierarchy problem. And I had said there were 3 things. 1, 2, 3. 1 was people are currently worried the order 1 numbers haven't helped in SUSY or composite Higgs, etc. In the models, people like to talk about the order 1 numbers don't help, but this is dimensional analysis, so the order 1 numbers could work in our favor if we want. I had said what appears at the scale dimensional analysis predicts, it doesn't tell you what appears there. What is true in many of these other models is, or in SUSY, etc., is new particles. But again, that is also dimensional analysis doesn't force this to be new particles. And then the final one was trying to evade dimensional analysis, which is just, this is actually what we've been focusing so far on, right? Relaxation, historical solutions, this is really what we've been talking about. I haven't talked about how to get show that you can get order 1 numbers in your favor instead of against us. And I haven't talked about, are there examples of making this scale harder to see? So what I'm now going to do is give a bunch of toy models that illustrate these 2 points. So toy models that show that these do not have to be true. They can work in other directions. So toy models. And so clearly, if you like any toy model, the way to go forward is then just apply it to the Higgs in some way, shape, or form. That has not been done yet, so I'm pretty sure people would be interested if there was some way to do it. Okay, so let's go over a few examples of how to get order 1 numbers in your favor instead of against us. So I think I have 2 models that do this, or 2 examples. Yes. Yeah, okay, so 2 examples of point 1 that order 1 numbers don't need to go in your favor. So first, let's be slightly more explicit on what order 1 number you need, right? When I say order 1 number, I have to then start saying a bit more about what are the order 1 numbers. And so here is a extremely crappy argument that people use. It is wrong because I'm going to be giving counterexamples, but this is part of the reason why people think they know what the order 1 number is. Well, I guess maybe the reason why they think they know the order 1 number is because they know it in SUSY, but this is let me just repeat the argument that is often given so we know what to beat, right? You need to know your enemy before you can find a counterexample. Okay, so I unfortunately need to write order 1 numbers, so I need to look at my notes. Okay, so let's say we have a Lagrangian with a scalar square root of 2 phi psi bar psi. We had said dimensional analysis says that the scale is of order m phi over the Yukawa coupling with some order 1 numbers. And let's write down a guess. Like I said, this is the standard guess. It's going to turn out to be wrong due to counterexamples. So standard guess people like to do is then just say, let's calculate a loop correction to this theory. This is a loop correction to the mass of phi. And it is minus y squared over 2 minus, from the fermion loop, I put a y over square root of 2 there. Integral d4p 2 pi to the 4th. Fermion propagators, trace I squared over p slash p slash. Okay. So what can we do? We're going to do this integral. I assume everyone's done it at some point in their life. This is what, minus 4 over p squared. This is, what is the phase space? 2 pi squared p cubed dp. And what we're going to do is just say, screw it. I'm going to evaluate this integral with a hard UV cutoff from 0 to lambda in Euclidean space. So I guess there's an I here that I've not been careful about. Let's see. And you get (4 over 16 pi squared). Okay. So great. Is this? Yeah. Okay. So people are going to be like, this is the scale you estimate with dimensional analysis. And I'm just going to say lambda equals m of a new particle is equal to m phi over y. There's a square root 4 pi, I guess. 4 pi squared. Took the absolute value. Okay. Great. Oh, crap. You're right. You are right. That should be 8 pi. Okay. Is that? I have it in my notes. Let me. Okay, I think my notes said that at least this part is correct. Possibility I did it wrong, but I think that's actually what people say. And so this is the order 1 number people associate, and this is people have decided fiat that the scale is equal to the mass of a new particle, and now they have decided they know what the order 1 number is. In fact, you could say this is the top quark, and then there's 3 of them. So you can even 3 colors. So if this is the top quark. So this is the standard argument now, as applied to the Higgs, before we start just giving counterexamples up the wazoo. Okay, I have found the best thing when dealing with people giving arguments like this is just to give a counterexample. Don't fight people on philosophy, just give counterexamples. But the argument there is if you put m phi equals 125 GeV, y equals y top, you get m nu equals 500 GeV. People are like, I do not see, or rather experimentalists do not see new particles at 500 GeV. Oh my God, standard model is tuned, it fails dimensional analysis, the world is about to end. Okay, obviously quite a few assumptions, assuming you know order 1 number, assuming you know what appears at the scale, et cetera, et cetera. Okay, so let's first show that, where are they? Those order 1 numbers are just counterexample it. Okay, we're going to go 2 examples. And for the hell of it, we're going to even work in the language of, and talk about the work of old famous people to show that they themselves are wrong. So, great. Counterexample number 1. If you actually want to get, I'm going to be a little bit blasé about this one. Raman Sundram has a nice set of lectures where he actually does this exact calculation. So go to Raman's lectures if you, lecture notes or TASI notes, I think, if you actually want to see the order 1 number exact calculations. But the idea is you have a 5D model with a circle. You have, great, you have a U1 with a massless electron. Okay. If you look from the 4D perspective, you have a U1 gauge field. You have the 5th part of the U1 gauge field, and then you have a Dirac electron. So you have an electron. We're going to be interested in this guy. People understand the mass of fermions. People understand the mass of gauge bosons. Here's the mass of a 4D scalar that we're going to care about. Okay. Great. Okay, so the Lagrangian is I psi bar d slash psi. D slash has, well, a partial slash. There's probably an I in the gauge coupling. Maybe it's a plus, I don't know. Choose the sign of the electron coupling to get my sign right. Minus I, G, A5, gamma 5. So there's the 5th dimension. And then I guess there's the 5th dimension derivative. D5 slash. Okay. We have a circle. The solutions to a circle are sines and cosines, right? We've done particle in a well and all this stuff. And so we know derivatives just give you n over your radius of your circle. N is just some integer. And, okay, I might be getting i's wrong or something. But, okay. And we have our scalar coupled here. So M effective is n over r, right? This is some number. It looks like a mass term here. Okay. We're just going to, well, I'm going to tell you what the Feynman diagram is. It'll take like the rest of the lecture to actually calculate it. So I would suggest just looking through Raman's lectures if you want the exact order 1 numbers. I'll do the other one, next one, a little more carefully so you can sort of see. But okay, A5 has a coupling to your fermions, A5, and here you sum over all the different fermions, sum over the different masses. These are sometimes called KK scales, KK fermions. It is messy. You have to make sure you regulate it correctly. And okay, great. I even have still the number up there that you expect doing this crappy cutoff calculation. And you get delta MA5 squared is minus 4 G squared over 16 pi squared, 1 over R squared, 6 zeta of 3 over 4 pi squared. The important thing here is to notice this equals mass of the first particle, right? N equals 0 is your massless fermion. N equals 1 is your first new particle. This is equal to 0.2. So if you need things to just say, actually, it can be smaller, you just point them to one of their favorite 5D models and whatnot, and just say, come on, it is easily possible to get a factor of 5 here. What happened? This 5 appears square root of 2 in the new square root of 5 in the new particle, easily pushes things out of range of the LHC. Well, 5 might not quite be enough, but the idea is clear. Argument is wrong. So you might be like, well, fine, 0.2 is maybe not the best. So let's do something even more extreme. Let's get a whole loop factor. Let's do an example which has a whole loop factor difference from what you would normally expect. Okay, I guess I can go up top here. Okay. Let's win by a loop factor instead. Okay. Great. This example is from Nima's G minus 2. And he explains it in a pretty crappy manner, so hopefully I'll give you a better way to think about it. Okay. So here's going to be my toy model. It's going to be an electron with U1. Electron. This is just going to be a toy model of what he did, and charged scalar. Okay, so as a toy way of doing the actual electron, E and M, and the Higgs. Okay, so the question is, let's say I am at low energies, and I see an electron dipole moment. Dipole. I see not only the dipole, if you want, you can pull out the piece here that's E sigma mu nu, E conjugate F mu nu, to make it obvious that I'm talking about the dipole moment. Plus E d squared, E conjugate, H dagger H over lambda dipole. What is this thing? It's not a dipole. Whatever, I'm just going lambda other. It is a two charged scalars. Maybe I should, well, whatever, leave it as H. This is cubed. Okay. So let's go through this and find the version of that argument that those people would apply to this guy. Okay. What they would say is you have an E conjugate, your H dagger, close this loop, and I generate from this guy, I generate this term. Close this loop. Again, I'm going to say you're going to win by a loop factor, so I'm going to be slightly sloppy again, and only care carefully about 16 pi squareds. This is 1 over lambda other cubed, some mass scale of new particles. This is a guess using their standard arguments. 16 pi squared should be equal to 1 over lambda dipole. Okay, so this is the standard argument. And we're just going to show a UV completion where this is 0, where we are able to generate actually a 2-loop factor here that's going to be this thing squared, relating the two, rather than a 1-loop. Okay, so UV completion. Okay. Let's see, I'm going to have to remind myself exactly. So I'm going to introduce 2 new particles, which are heavy, S, N, and then they're right, S conjugate, N conjugate. Hopefully people at least have seen this particular way of writing Weil notation of conjugates on fermions to write their left-handed and right-handed pieces. But okay, so the Lagrangian I'm going to write that generates that UV completes this guy is going to be E H, the Yukawa coupling times S conjugate N conjugate. So what I'm going to do is write everything within a notation where there's an SU2 under which these guys are doublets. Right? This is just a notational thing because it'll make zeros a lot more apparent. If you want, you can even make sure, in Nima's version, there are symmetries forcing these zeros. And so, okay, there's going to be E conjugate, H dagger, S, N. This Yukawa coupling would be 0, YR. And then finally, the mass term, Sn, Sn, and what did I choose? Ms, Mn, and a Yukawa coupling with the Higgs. Okay. So if you want, I can talk afterwards about how you can put in an SU2 and flavor symmetries and whatnot to set these things equal to 0. For now, let's just take them to be 0. And the question is just, let's try to get these 2 guys, right? Okay. Let us first, again, so this is the computation you actually do, and then we're just going to bypass it by not needing to do a computation. So if you want to get the dipole moment, the first term, you do E. What does E turn into? E turns into S conjugate. Whoops. S by your charged Higgs. Comes back, you emit a photon, and you come out E conjugate. This is S and N, etc. Okay, so you could just go through this diagram, put in S, put in N, maybe diagonalize the mass matrix if you feel like it, etc., etc. Okay. I'm a dimensional analysis person. Let's just write out what the answer has to be. Yukawa on the left, YL 0. It's dimension 5, so this is going to be 1 over the mass matrix. And then Yukawa on the right has to be great. Okay. Now, what is the inverse of a triangular matrix? Right, that's triangular, it's 0. Turns out it's also a triangular matrix. So do I have the answer somewhere or another? I suppose I do. It's a math theorem in case you are wondering. Triangular matrices have triangular inverses. So this has nothing special here to do with two particles or anything like that. This selects out the first row. This selects out here. And what do you know? We have a 0 here. So this is equal to 0. Simple. I don't even have to do a calculation. You can ask, when does this fail? If I have logs and other crappy stuff like that. And so a lucky thing is that this thing does not have a log. You need to introduce other things, go to to loop and things like that to get logs. Okay, great. This is 0. This means if we want, it's going to be, okay. So how not to do this calculation? We have 15 minutes. Okay. How to confuse ourselves? Let's confuse ourselves a little bit by diagonalizing that mass matrix. I have some new S n primes. Let's use little s's and little n's. S n is some rotation matrix times S n. And the same thing for their conjugates. Oh wow, my cursive s's look a lot like rows. Some other rotation, prime, S conjugate, and conjugate. And then what do we get? This diagonalizes the mass matrix. S, n, m little s, m little n, 0, 0. S conjugate, nope, it's the little dudes. The rotation matrix scrambles up these Yukawa couplings. So we get y1, y2 times S conjugate, n conjugate, EH, E conjugate H dagger, S n, call this y3, y4. Okay, I've erased a lot of the stuff I shouldn't have. Oof. Oh well. Let's commit to a bad decision. Okay. So now look at this and rewrite the same thing here. What does it look like? It looks like I get y1 over ms times y2, no, y1, y2, y3, e d squared e conjugate, plus the next term, y2, y4, 1 over mn, e d squared e conjugate. None of these things are 0. This is not 0, this is not 0, but we just showed that the sum of them is 0. So if we look at it like this, we see we have a very weird situation where one heavy guy's contribution is non-zero and is canceled by another guy's contribution who has entirely a different mass, right? So this looks extremely confusing because this integral, whatever you integrate to give you here as a function of momenta, some contribution here at Mn has exactly a negative contribution here at Ms that exactly cancel each other, and you get 0, right? From the EFT point of view, you get something quite crazy. Is how the hell do two things cancel exactly? It's because, well, you took very specific SU2 structure here, which is rotating two guys of different masses into each other. So if you see just one particle, you don't see the full symmetry of this theory. You need to see both of them. So if you miss a symmetry, you can get very surprised. Okay, so this shows that at one loop, things are non-zero, or things are 0. So let me keep that and just say 2 loops. Draw any old crappy 2-loop diagram here. What else? Whatever. Draw something 2 loops. You're going to get logs, and it's going to be non-zero. So this means you have 2 loops, 1 over 16 pi squared, e d e conjugate, over whatever typical mass scale in the problem is. Let's just choose all the fermions and everything to have the same mass. Just call them the same mass mu. Okay. This was only half the problem. Let us now look at the other operator, which I have since ignored or erased. And we're going to draw a tree level diagram. H dagger. And there's going to be some mixing between the two S's. This is going to be like S or N or something like that. But since we're doing things in SU2 language, this is the SN combined object. Okay. Tree level, it's going to be non-zero. Again, I'm lazy. I'm not going to do this. I'm going to get it by dimensional analysis. This is dimension 1, 2, that's 3, 4, 5, 6, 7. So it's 3 m's in the denominator. No, let's keep that. Let's go here. Erase our shame. Okay. And okay, let's just, again, it must have YL 0, 1 over m cubed. What is the other? 0 YR. Now let's be a little bit careful about this m cubed. This is SU2 symmetry. Mass transforms left times right. So this is really 1 over m dagger, m. Okay, let's just multiply out m times m dagger times m. Main thing is that there's no zeros. So here's my matrix M, A0, B, C, times M dagger, A, B dagger, 0, C. You can hopefully see I'm just being lazy here because my main point is to show things are very non-zero. So I'm just calling them A, B, C. A0, B, C. This is M dagger, M. Let's see. A squared. And hell, let's just take everything real since I'm lazy and don't want to write M daggers or daggers. a squared, ab, ba, b squared, c squared, times a0, b, c, a cubed plus ab squared, abc, a squared b plus b squared a, b squared c plus c cubed. Okay. The inverse of this matrix clearly has no zeros, right? These are just random numbers. The inverse, there's nothing special at all about this guy. M inverse is just going to be some random crappy matrix. So we're going to get YL0, some crap, 0YR, which is clearly not equal to 0, right? And so this is not equal to 0. And the term that everyone would be like, oh, you close one loop and then you get something that's one loop suppressed, is clearly two loops suppressed, not one loop suppressed. And in fact, you can even show that this has to be a log here of, let's say, ms over mn or something like that, etc. Okay. So what have we found? We have found that the dimensional analysis works, but again, you cannot estimate order 1 numbers, right? Here we're off by an entire loop factor, right? Off by a factor of 100 if you're just doing dimensional analysis, because, well, dimensional analysis does not give you order 1 numbers. This is the entire thing, right? And so, okay, it's an entire loop factor times a log. Logs are, pretty much all logs are 10. Doesn't matter what you're taking a log of. And so it's probably closer to a factor of 10 off than 100, but that's sort of besides the point. The point is, you cannot estimate order 1 numbers, and here's yet a second counterexample to it. Okay, so great, or maybe not so great. It depends on what side you're on, but statement, order 1 numbers can be very different, and you'll notice when, let's say we finish writing let's quantify how off you would be. Other people would have guessed 1 over, this guy is 1 over m cubed times the Yukawa couplings. Let's just set everything to 1 times m new particle over 16 pi squared is equal to 1 over that thing. 16 pi squared, 1 over mass of the actual particle. Wait, why did I put a loop factor here? That's tree level. Okay. So they would have guessed m new particles is equal to the actual mass of the particle over 16 pi squared, which is obviously wrong because the model has masses of new particles at m, not m over 100. So if you're trying to do these estimates, be aware that when people say that, like, oh, there must be new particles in the standard model at 500 GeV, dude, you can get the order 1 numbers wrong. It could be 5 TeV, who knows, right? Okay, all right, so I don't have enough time for another example. Do people have any questions about this? Yeah. Mm-hmm. Yes, that's right. So, but you can argue all you want with philosophy. I say if I have a math counterexample, I don't care about your philosophy. Your example is wrong, right? You don't need to say, argue against people about philosophies if you have a counterexample. Yeah, so yeah, that's why, I said that was the argument. I'm not going to defend it. I'm give a counterexample. A counterexample is better than saying your philosophy is wrong, because people will never agree on philosophy. Math they can agree on, and if you just give them a mathematical counterexample, there's nothing they can do, because everything is physical, everything is calculable. You can forget their logic. You can just say, this is the result that you think is true. Counterexample. I don't care about your logic anymore. And so if their logic for trying to get order 1 numbers, I know is wrong because I have a counterexample. I don't need to say why the logic is wrong. I just say, counterexample, leave me alone. And that's the best way to argue with someone. You don't argue about their philosophy where you may not agree. You choose something you do agree, math, and then show that they're wrong. Yeah, and so I would agree, yes, there are philosophical arguments against it, but there's a better than philosophical argument, which is what I'm trying to get at here. Yeah. All right. If there's nothing else, remember we have the photos right now. So gather in the little thing in the center there with the garden, and we're going to all get our picture taken.